What's DOM look like? Well, I hear yawns, I hear somewhat descriptions. What I was actually going for was it looks kind of like a volcano. If you were to plug in some numbers for x, you would find, or actually if you just graphed it on your calculator even, you would find that it looks something like this with a better curve in it. But something like that. 1 over x squared looks like this. And we're looking at 2 different parent functions today. We're looking at 2 whole new functions. One is 1 over x squared, which looks like that. And the other is 1 over x, which actually looks almost the exact same, except instead of there being a square in it, making it always positive, it'll just be 1 over x. So this part will be down here. And it'll look like that and that. And that's essentially everything that we're looking at today and how we were to graph those 2 functions. So, make sure you get your homework turned in if you haven't already. And we are going to start 2.6. What? No. We have done this before. What is the trick to finding these domain problems? Yeah, find what makes the denominator equal to 0. Number 1, all real numbers except for 4. What about number 3? 5 and negative 4. It's just everything that's going to make the denominator equal to 0. Very good. And the last one doesn't have any. Well, imaginaries don't really count. So all real numbers. Very good. Now, today, one of the things we're going to be talking about today are asymptotes. And an asymptote on a graph is basically it's an imaginary line that your function runs right along next to but never actually touches. So like this DOM we did has a vertical asymptote at x equals 0. You see how on that vertical line the function is going to ride right along next to it but never touch it. Same thing, we also had a horizontal asymptote at y equals 0 because again our function is going to run right along next to it and never touch it. And I'm going to be showing you how to find these vertical asymptotes and these horizontal asymptotes. And then we even have something called a slant asymptote. Now, vertical asymptotes are the exact same thing as the domain. Everywhere that you have something that can't exist in the denominator, that's going to form a vertical asymptote on your graph. So, let's just flip over to the next slide. Oh, just kidding. We'll come back to that and that. Find the vertical asymptotes. That's everywhere that x cannot be. So where's this one going to have a vertical asymptote? What's this one? And 0. This one wouldn't have any. Now 25, here's the one place where vertical asymptotes and just domain are different. The one place where vertical asymptotes and domain restrictions are different are, what cancels in 25? The x. Now, if I was asking you for the domain, you'd say everything except for 0 and negative 4. And you'd be right. However, when it comes to vertical asymptotes, if something would cancel, then it no longer forms a vertical asymptote. It's just a little blip, a hole in your graph. So actually, 25 would only have a vertical asymptote at negative 4 and not the 0. Whereas 23 would have one in both, the negative 4 and the 0. Raise your hand if you'd like a further explanation about why one of them does and one of them doesn't. Okay? Yes?
Okay, I'm confused. Why wasn't the x cancel out?
Because this one's bonded by addition.
Okay.
Good question. Now, before I go any further, I evidently skipped some key points, so let's go back and look at those. These say, as x approaches, here's how you read this. -3 from the left-hand side. So where's -3? Here it is. From the left, as we get closer and closer to -3, does our graph shoot down or up? Down. From the left-hand side, this right here indicates the left-hand side. Our graph shoots down towards -infinity. This says, as x goes towards -3 from the left, our y value goes towards -infinity. What about +1 from the left-hand side? Goes down again, -infinity. What about as x shoots off toward -infinity, as our function tails off, what y value does it look like it's just going to eventually home closer and closer to? Wow, very good. That's correct. Not much explanation needed. What if it had said -3 from the right-hand side? Yeah, +infinity. -3 from the right-hand side shoots up toward +infinity, or +1 from the right-hand side. +infinity. Very good. Well, let's look at some more. What about as x approaches +1 from the right-hand side? Who can answer that? Can you answer that? Oh, I bet you do. You just don't want to say it. Who can tell me? Yes, ma'am. Very good. +1 from the right-hand side, which is what the plus indicates, means, and it's shooting up toward +infinity. What about -2 from the right-hand side? Clint. -2 from the right-hand side. That's exactly what it would be. Here's -2 from the right-hand side, -infinity. What about as x shoots off toward infinity? What y value is our graph leveling off at? 1. As x shoots off toward infinity, what y value is it kind of riding right along next to? That would be 1. These are both vertical asymptotes. This is a horizontal asymptote. That's how they affect your graph. The very last thing we're going to do today is I'm going to just show you a function, and you're going to have to find all the asymptotes, and then using nothing but the asymptotes, you're going to have to graph that function. So let's say all you knew were all the dotted lines. The only possibilities are, over here, it's either going to look like this or like this. So you can just plug in any of these points and figure out, is it up here or down here? And you can figure out whether it's this or that. This one had to either be like this or like this. Again, how do you know? Well, just plug in a value for your function and see, is it down here or is it up here? So we'll do all this later, but when you have your asymptotes, you have the basic shape of your graph right in front of you. All you have to figure out are maybe 1 or 2 extra points. Okay, we already did this slide. Vertical asymptotes. If you want to make a note somewhere in your notes, all it is where your denominator equals 0 that doesn't cancel. If it doesn't cancel and it equals 0 in your denominator, it forms a vertical asymptote. And all vertical asymptotes are of the x equals persuasion. So this is x equals -4. That is the line that forms your vertical asymptote. X equals 0 and x equals -4. X equals -4. And no vertical asymptotes. Well, definition's probably not how I should have worded it. Does somebody have their book open? It'd be awesome if we could just restart the book. Ryan, your book's open. 2.6. Find the word vertical asymptote and read aloud what it says. You can find it for me. Vertical asymptote. Who can discover that for me? 2.6. What does it say?
The line x equals a is a vertical asymptote of the graph of the function f x.
So why don't I just give you a definition?
Yeah.
Okay, it's where the denominator equals 0 that doesn't cancel. Because if it cancels, like, let me give you another example. What about something like, I'll give you a harder one that you might see today, like x minus 3 over x squared minus 9, okay? You might be able to think, hey, this factors into x plus 3x minus 3, so plus and negative 3 are going to be vertical asymptotes. But which of these cancels? The x minus 3. So actually, your only vertical asymptote would be negative 3. So, there you go. Vertical asymptote. Any further questions on those? Horizontal asymptotes. We're going to make a hack chart. A horizontal asymptote chart. Horizontal asymptote chart. Because there's only 3 possibilities. Yes, you, yes. Yes, yes, you, yes. The only thing that matters when it comes to horizontal asymptotes is your highest exponent. That is the only, and why is that? Because a horizontal asymptote, let's think about that. What the heck is that? That's as x shoots off to positive and negative infinity. As x gets bigger and bigger and bigger on your graph, like as x equals 1 million and negative 1 million, eventually, as you plug in bigger and bigger numbers for x, let's put it this way. A billion, let's say we plugged in 1 billion for x here. 1 billion cubed is literally 1 billion times bigger than 1 billion squared. As you put in astronomically large values for x, eventually the highest power is just going to kind of dictate everything. So, that being said, here are the 3 possibilities. The only 3 possibilities are that your highest power, which is kind of like the only column in this chart, we're looking for our highest power. The only 3 possibilities are that it's in the numerator, the denominator, or that it's in both. And I'm going to tell you H-I-G-H-E-S-T. It's just H. There we go. And this is going to be where your horizontal asymptote. I'll tell you, depending on whether your highest power is in your numerator, denominator, or both, will depend on where your horizontal asymptote is. Now, let's think of an example of a function where it's in the top. X squared. That's the same as x squared over 1. And x squared over 1, the highest power is obviously in the numerator, right? The x squared. Does x squared tail off anywhere, or does it just kind of keep shooting up to infinity? It just shoots up. It doesn't tail off anywhere. When your highest power is in the numerator, you're going to have no vertical or horizontal asymptote. When your highest power is in the numerator, you will have no horizontal asymptote. Now, what about, well, if it's in the denominator, if your highest power is in the denominator, then as x gets bigger and bigger, your denominator is going to get bigger and bigger than your numerator. So, a fraction whose denominator is much, much bigger than its numerator, let's think of an example, like 1 over 10,000. What number is this really, really close to? Yeah, that's 0.00001. If your highest power is in the denominator, then your horizontal asymptote will immediately and automatically be y equals 0. Period. End of story. Now let's think of one where it's in both places, like number 35. Number 35. Let's just think about this for a second. If I plugged 1 million in for x, what would that be? That'd be negative 2 million plus 1, which is practically still negative 2 million, over 3 million plus 5, which is practically 3 million. What does negative 2 million over 3 million reduce to? Negative 2/3. No matter what you plug in for x, if the variables are of the same degree, then eventually nothing else will matter. All that matters is this. And what does that reduce to? If this was your entire problem, what would that reduce to? Negative 2/3. When your highest power is in both the numerator and denominator, then your horizontal asymptote is nothing more than the quotient of your leading coefficient. Leading coefficients. So, let's put this into action. 29, where's our highest power? Consult your chart. What's your horizontal asymptote? Y equals 0. Done. 31, where's our highest power? Both. What does that reduce to? Your horizontal asymptote is y equals 4. That's it. 33, where is it? So, 35, well, we already talked about 35. Question. Horizontal asymptotes are simple. There will only ever be one, and there could only be one, because as your function can't level off in two places, that wouldn't be a function. It can only level off once. That's why there's only one. Questions about leading coefficient. Quotient of leading coefficient. Coefficient. Plural. Let's do it. Questions on those? Vertical, horizontal, check, check. Yay. Okay. Well then, here we go. Use transformations of our two parent graphs to graph these. Now there's two ways to do these. Two ways. The easiest way is to just, I say two ways because you could just find your asymptotes for both, graph them, and then plot your points around them. However, the easiest way to graph these is to know what the parents look like. So I'm going to take a moment to draw the parents down here at the bottom. And you probably want to make some sketch of them in your notes somewhere. I'll do 1 over x. And I'll do 1 over x squared. Okay. 1 over x looks like this. Doesn't even have to be perfect. And 1 over x squared, like we did in the DOM, looks like this. Although, theoretically, it'll be closer to the asymptote, but whatever. Now, both functions, both of them, have natural asymptotes. Well, think about it. 1 over x and 1 over x squared, where's their highest power? Denominator. So they both have, what the heck is that? They both have a horizontal asymptote of 0. So I'll just kind of draw this one all the way through. They both have a horizontal asymptote at 0. And they also both have a natural vertical asymptote at 0. So there are both of their natural asymptotes. Well, that's really bad. I need to move that one. Okay. There's both of their natural asymptotes. So it's very simple to look at these and figure out which parent you're dealing with. 1 over x, 1 over x, 1 over x, 1 over x squared, 1 over x squared, 1 over x squared, etc. Now we are just going to use those parents, and then we're going to use things we've already learned about the shifting of graphs to just shift our asymptotes and then graph around them. For instance, the parent function is 1 over x. Now, first of all, do you see the difference between this problem and this problem in the way that they're adding and subtracting? 37 or 39, which one of those do you think is going to have a vertical shift? 39. Just like the old function, whenever something is added or subtracted outside the function, that causes the vertical shift. Whenever something is added inside the function or subtracted, that's a horizontal shift. So, where is this one shifting? To the right by 1 unit. It's just like x minus 1 squared. Remember how we graphed a lot of those? Whatever is inside here, what's going to make that equal to 0? 1. So it's going to shift from right to positive 1. So if you were to graph that, and I'm going to oh so quickly sketch these, and that's all you have to do for these is sketch them. Okay? it would help you if you just kind of drew in your new vertical asymptote was shifted right 1. Your horizontal was not changing. So then you just graph your parent around your asymptotes. Your parent of 1 over x was down and then up here. And you've correctly graphed it. It's the same as the parent, just shifted right 1 unit. What about the next one? Where's that shifting? Up 2 units. So again, yeah, it's low on space. I'll just take it elsewhere. So taking our parent, now I know you don't have all these handy dandy little tools, but nonetheless, this is essentially what we're doing. So our original 1 over x had these asymptotes, but we are shifting where? Up 2. So I'm going to take my horizontal, shift it up 2 units, and now I'm just sketching my parent around my new asymptote. My parent was 1 over x, and there you go. See how I just shifted my asymptote? That's the easiest way to sketch these. Oh yeah, it's completely backwards actually. Thank you. I was thinking negative 1 over x. Wow, that's not good. Thank you, Martha. Yes. All right. There you go. Thank you. Let's see. Let's put them together. 41. 41 has 2 shifts. And what be they? Whoa, I hear so many things. Eeny, meeny, miny, Lazarus. What do I do? Very good. Left 1, down 2. So I'm just going to take my asymptotes. Shift it left 1, shift it down 2, and now I just graph my parent around those. I almost did it again. What's the wrong with me? It's obviously not supposed to curve out like that, but whatever. And all I really need to see is that you've shifted it correctly and then the general shape. The 1 over x squared ones are the exact same, except they're both going to be going upward. So let's just pick one of those. 43, 45, 47. Pick one. 47. So I'm going to draw my normal axes. Whoa, that's too big. Black. There's my axes. Draw my normal asymptotes at 0 and 0. Now, Nate, where are my shifts? Up 1. Very good. Up 1, right 3. Now, it's 1 over x squared, so the only difference is this one is kind of volcanoing instead of being opposite of each other. Only difference. Questions about graphing these functions? That's as complicated as they get, I think. Yes. Yes, I did. Yeah, just like a normal horizontal shift, it's basically whatever makes this part 0, which is positive 3, which is why it goes to positive 3. Other questions? All right, let's just skip on ahead then. I already did all those. Okay, last slide. Really? Already? I feel like we've skipped something. Okay. Okay. Slant asymptotes. Slant asymptotes. Now, you will only have a slant asymptote. A slant asymptote is basically an imaginary sloped line that you're going to ride right along next to. And you will only have one of those when the top is exactly 1 power higher than the bottom. Because as we just learned a second ago, none of these are going to have horizontals because they're all on the top. But if it's exactly 1 power higher, then that means it kind of naturally reduces down to just 1x, which is a line. So to find your slant asymptote equation, all you have to do is divide it just as it is. And yes, you're going to have to do long division. So 71. That's not a square root. I know. Plus 0x minus 1. What's x squared divided by x? X. Multiply it back through. X squared. Subtract. That's just 0x. Now, is the negative one a remainder? Yes. If this has a lower power than this, then it's a remainder. Here's the nice thing about slant asymptotes. You don't have to worry about the remainder. So this has a slant asymptote equation of y equals x, which is just that straight diagonal line going through the origin. Bless you. 75. What's an easy way to divide that? Well, actually, you probably could do that, but what's another easy way? Synthetic. That's right. Whenever it's just x plus or minus a number, you can just divide it synthetically. 1, 1, negative 6. Drop, multiply, add, multiply. We don't even care about the remainder. What's my depressed polynomial? X plus 4. That is your slant asymptote equation. And 77, you will have to do long division for. In fact, we can do that real quick. Here's the thing. Because they're all just 1 power different, you should only have to do 1 or 2 steps every time. Plus 0x squared plus 0x plus 1. X squared divided by x cubed. X, thank you. I guess I said that backwards. Multiplying it back through. X cubed plus 2x squared. Subtract. 0x squared minus 2x squared is what? Negative 2x squared. What's negative 2x squared divided by x squared? Negative 2. Now I can stop right there. Everything else is just going to be a remainder. You'll only ever have an x in a number. Maybe a 3x in a number or something. So here's our slant asymptote. Now you might be thinking, okay, I've got it. Now what the heck do I do with that? Here's how you would use a slant asymptote to graph a function. And in fact, I believe these directions say, follow the 7-step strategy. Okay, you don't have to use 7 steps. It's not that hard. Here's all you have to do to graph these functions, and you are going to have to graph them today. 77, I'll graph that one. Here's my axes. My slant asymptote was x minus 2, correct? Yes, yes. So, x minus 2, what's the y-intercept of that function? And what's my slope? Positive 1. So that's approximately that line right there-ish. Y-intercept of negative 2, slope of 1. That's just a line, x minus 2, except I made a dot. It's only an asymptote. Where do I have... Yes. Well, no. We're graphing the whole thing, but what you're going to do is just put your asymptotes on the paper and then graph around them. It's not that bad. This one, what's going to make this guy equal to 0? Ooh, I heard both the answers. What could I factor out of this? X. Leaving me with x times x plus 2, right? So what are my vertical asymptotes? Negative 2 and 0. Very good. So at 0, at negative 2. Now, there's my asymptotes. I just have to graph around it. There's only 2 possibilities for both places, for all 3 places. First thing, there's only 2 possibilities here. It's either going to come up like that or be down like that. So how do I know which one it is? Just plug in a number. What's a number less than negative 2? Negative 3. If when I plug in negative 3 I get a number up here, then it's going to look like this. If I get a number down here, it's going to do that. Those are the only 2 possibilities. It has to go along your asymptote. So plug in negative 3. That's negative 26 over 9 minus 6. So negative 26 over negative 3 is a negative number. Well, how much negative? Hold on. It would help if these were accurate asymptotes. The asymptotes?
Yeah, that's the one. I got that.
These are the verticals. We factored the bottom into this. Remember, the vertical is wherever the denominator is 0, so 0 and negative 2. This is where it kind of stinks not to be an accurate grapher. Now I'm not entirely sure what points these are. Let's see, this was what, negative 2? That makes this little intersection point, if x equals negative 2, that makes that little intersection point negative 2, negative 4. If I plug in, what was this, negative 3? Negative 3 cubed is negative, plus 1 is negative 26. Negative 3 squared is 9 minus 6. Positive 3. So what is that, negative 5 1/3? Yes, it is. Negative 5 1/3 is here. So that means I'm below my asymptote. And that's going to be the first part of my function. Now I'm looking in between these. What's the number between 0 and negative 2? Negative 1. Let's plug that in. That'll be negative 1 plus 1 is 0. Well, what's 0 divided by anything? Which means I have a point right here. Which means I have to write along my asymptotes above my slant. Ish. I hope that's accurate. All I'm looking for is general shape. And now we just need to know this piece over here. What's a piece greater than 0? 2 or even 1. So I plug 1 in. That's 1 plus 1 is 2. 1 plus 2 is 3, so 2/3. 1 comma 2/3, so I'm going to be above my asymptotes. And there's my function. All you need to know, am I above or below? I was below. Am I above or below? I was above. Am I above or below? I was above. So there's your function. I'm sorry, say one more time. You just plug in a number on in between, any number less than negative 2, any number greater than 0. It'll either be above or below your asymptote. And the only one that was really hard was this one, because it was so close I couldn't tell, but when I graphed it more accurately, I found out it was good. Questions? Okay. There you go. I'm actually going to take off the screen part. I'll tell you what. Slant equations only, which means you don't have to graph all of 72 through 78, but I do want you to graph 78. You do not have to graph all 4 of those, just graph 78. And you do have to graph all the 1 over x problems, those ones that all we did was shift them. But you don't have to graph 3 of those last 4.